We're going to start by working through some problems of molecular compounds, starting with going from name to chemical formula, and then chemical formula to name, and then we'll follow that with some ionic compounds going in both directions as well. When we look at the name of a molecular compound, we see that it consists of two words. The first word has to do with element 1, and the second word has to do with element 2. And these elements may or may not have a prefix attached to them. In the case of this first example, both elements have a prefix. I'm going to rewrite these, showing the color coding for the prefixes and the elements, and that way we can see how the different parts of the name are separated. So for the first element, we can see that there is a prefix of di. First element is phosphorus. For the second element, prefix is tetra, and the second element is shown as its element or root plus ide as hydride. For the first element, remember that it takes on the full element name right off the periodic table with no modification. So phosphorus simply has the symbol P. For prefix 1 is di, and that leads to a subscript of 2. So for the first part of this chemical formula, we have P2. Moving on to the second element, our root plus ide is hydride. The root is hydrogen, and that means that the symbol is H. And prefix 2 is tetra, which gives us subscript 2 of 4. So the chemical formula for diphosphorus tetrahydride is P2H4. Our second example is boron trichloride. So we'll do something similar with the color coding before we then move from name to chemical formula. You can see that there's no prefix for the first element. We simply have element 1 of boron. For our second element, we do have a prefix, prefix 2 of tri, and our root plus ide is chloride. Once you're able to separate the parts of element 1 and element 2, and you have learned the prefixes and the root plus ide names, working with molecular compounds becomes pretty straightforward. So now, element 1 is boron. That has the symbol B. There is no prefix 1, so there is no subscript 1. Element 2, root plus ide is chloride. So chlor is for chlorine. That has the symbol Cl. And our prefix 2 of tri gives us a subscript of 3. So boron trichloride looks like BCl3. Again, if there's no prefix, then you just leave off the subscript. There is no subscript. One more example of molecular compounds going from name to chemical formula. We have ditellurium fluoride. So color coding our prefixes and our elements. We do have a prefix 1 of di, and our element 1 is tellurium. We don't have a prefix 2, but our element 2, root plus ide, is fluoride. So translating this, tellurium has the symbol Te. Oh, I forgot to highlight it. Has the symbol Te. Our prefix that goes with tellurium is di. That gives us a subscript of 2. Our element 2, root plus ide, is fluoride, corresponding to fluorine. So that has the symbol F, and we don't have a prefix 2, so we don't have a subscript 2. So we just leave it like this as Te2F. Going the other way for molecular compounds, our first example is NF5. Notice that for element 1, we don't have a subscript. The symbol for element 1 is N. We'll leave off the subscript because there's not one showing. Element 2 has the symbol of F, and subscript 2 is 5. So now when we go from chemical formula to name, remember, element 1 takes on the full element name, and element 2, we have to modify it as root plus ide. Again, if there's no subscript showing, then we just omit the prefix. There won't be any prefix. So going in order, there's no subscript 1, so we have no prefix 1. The symbol for element 1 is N, so that's nitrogen. We write the full element name. Element 2 has a subscript of 5, which is penta. So our prefix 2 is penta. And our element 2 symbol is F. That's for fluorine, but element 2 takes on root plus ide, so we write that as fluoride. Nitrogen pentafluoride. I guess better late than never here. There's my element 1, my symbol 1, and my prefix 2, and my element 2. Se2, S6. Both of these have subscripts, which means both elements will have prefixes attached to their name. There will be a prefix for element 1 and a prefix for element 2, where element 2 takes on root plus ide as far as the element name goes. If we color code this, our first element symbol 1 is Se. Subscript 1 is a 2. Our second element is S, symbol S, and our second subscript is a 6. So now we'll directly translate between the subscripts and prefixes, and then element symbols and appropriate element names. The first subscript is a 2 that gives us the prefix di. Our first element symbol is Se, and that is for selenium. Just a reminder, first element takes on the full element name, unmodified, of selenium. And when we write this next to the prefix, it becomes a single word. In this case, diselenium. Moving on to our second subscript, subscript 2, is a 6, and that corresponds to the prefix of hexa. And our second element, S, is sulfur. We write that as root plus ide, so it becomes sulfide. And the name of our compound is diselenium hexasulfide. Our final example for molecular compounds, S7O2. Just like the previous example, both elements have subscripts attached, so that means there will be prefixes attached to both parts of the name. Rewriting this with pretty colors, first element symbol S, first subscript is a 7, second element O, and second subscript 2. So now going from chemical formula to name, subscript 1 is a 7. That gives us the prefix hepta. Element 1, the symbol for element 1, symbol 1, is S. Now last time, in the previous example, we also had a sulfur, but sulfur was element 2, which meant that we modified the name. But here, sulfur is element 1, so it keeps its full element name without modification. And our first part of the name is the single word heptasulfur. Our second subscript is a 2, which gives us the prefix di. And our second symbol, symbol 2, is O for oxygen. But because this is element 2, we have to write this as root plus ide, and it becomes oxide. So our full name is heptasulfur dioxide. In the next set of examples, we'll go through ionic nomenclature. Now, this differs from molecular nomenclature because with the molecular compounds that we just looked at, there were no ions and there were no charges. It was a simple and direct translation between subscripts and prefixes and the element symbols and how we were naming those element names, whether full element name for element 1 or root plus ide for element 2. With ionic compounds, because they're ionic, they contain ions, and now we do have to make sure we're keeping track of ions and charges. So our first example is zinc nitride. One thing to remember about ionic compounds, and that is they also consist of just 2 words, and the first word is always the cation name, and the second word is always the anion name. So the key, the absolute key to understanding ionic nomenclature is knowing the ions. If you understand the ions, then it is a simple process to write down the names of the ions or to figure out the symbols or formulas for the ions, depending on which direction you're going. Here we're going from name to formula. That means we have to start with the cation name and the anion name, and from these names extract what do the symbols or chemical formulas look like. Okay, so what does that mean? Well, let me start with the color coding. So I'll write the cation in red and the anion in purple. When we go to write the symbols or formulas and charges, we need to go through this assessment so we determine if the charges are given to us explicitly, or if we just have to know them, or if we just have to know how to figure them out. So we'll see we'll see all of the different situations as we work through these examples. So for the cation, we know, oops, wrong color. So we can start by writing the symbol. Zinc has the symbol Zn right off the periodic table. And now we have to figure out what is its charge. So just as a quick reminder, the check that we do at this point is we ask ourselves, is our cation group 1A, 2A, 3A, cadmium, or zinc? If so, if our metal cation falls into one of these categories, then the charge is fixed. And what that means is the charge is always this single value. It never changes. And we just have to either know it, like cadmium and zinc, or we have to remember that the group number will tell us the charge. Group 1A is a 1 plus, group 2A 2 plus, group 3A 3 plus. In this case, our element is zinc. It has a fixed charge of a 2 plus. It will never be anything other than a 2 plus. Okay, and this is a pretty short list to have to scan through to determine, is our charge fixed or is it variable? If it's variable, we might have to figure some things out. So you always want to do that check first. Cation, it's done. We don't have to do anything else with it. Moving on, nitride. Pay close attention to the ending of the anion, because IDE endings are typically monatomic ions off the periodic table, except for cyanide, whereas our ITE and ATE endings are polyatomic ions. And your polyatomic ions are on your list from a long time ago, and there are some quizzes attached to learning the polyatomic ions and their charges. But the ITEs, ITE, and ATEs, ATE, those endings for the anions are polyatomic. So nitride, as opposed to nitrite or nitrate, nitride is a monatomic ion directly off the periodic table. The root tells us it's nitrogen, and the IDE tells us it's an ion, in this case because it's an ionic compound. And nitride has the charge of 3 minus. So this corresponds with anions in group 5A, 6A, and 7A having charges of 3 minus, 2 minus, or 1 minus. So again, the group numbers and the charges of the ions when those elements are ions, those are things that you just need to know that you can get from the periodic table. So we have now written our ions with their charges, and that is the biggest deal with ionic nomenclature, because once you get here, like I said earlier, it is simply writing down the name of this zinc ion and the name of the nitride ion. And I just went backwards, so let me try this again, because we're going the other way. We're going from name to formula. We already had the name, I realized as I was saying it. So let me say that again. It is still a very big deal. That part is still the case. But now that we have our ions and their charges, we can determine how they combine. So the next question that we ask, and you want to make sure that you check this every time, and that is, are the charges equal and opposite? And what I mean by that is, are the values of the charge the same? So I compare the 2 from the 2 plus of zinc and the 3 from the 3 minus of nitride. And what I want to know is, are those equal? Well, the answer is no. 2 does not equal 3. And why we care about that is because it leads to the next part, which is how we're going to combine these ions. So 2 is not equal to 3. That means that I have to take the charges, or I should say the values of the charges, and swap them out so they become subscripts. So I'm just rewriting the ions so I can show you how that's done. So what I mean by that is, the value of the cation charge, the 2, is going to come over here and become the subscript for the anion. And the value of the anion charge, the 3, is going to move over here and be the subscript for the cation. So when we rewrite this, we end up with zinc Zn3 N2. The reason this works by swapping out the values and making them the opposite subscripts, the reason that this works is because the sum of the charges has to equal 0. And we've learned this previously, but it's the same principle. So if I show you how this math works out, you don't have to check it every time. Looking at my formula here, I have 3 zincs. Oops, let me try this again. I have 3 zincs where each zinc has a 2 plus charge, plus 2 nitrides where each nitride has a 3 minus charge, and the sum of those charges has to equal 0. So I have plus 6 minus 6 equals 0, and so it works out. So we'll move on to the next example. Our next example is chromium 6 hydroxide. Again, when we're writing the name always consists of 2 words. The cation is the first word, the anion is the second word, and there's no space between the element and the Roman numeral. I probably could have written this a little bit closer, but the only space is right here between the cation name and the anion name. I'm going to rewrite this. So I have chromium 6 as my cation and hydroxide as my anion. Okay, so I'm going to do the same thing I did previously. My cation, my metal, is chromium, and that has the symbol Cr. And then I can run through that same list that I ran through a little bit ago for cation charges, group 1A, 2A, 3A, cadmium, zinc. And chromium doesn't fall into those categories. But in this case, I really didn't have to run through that because I already know what the charge is. The Roman numeral is equal to the charge. So you quite literally register what that number is and write it down as the charge. There's nothing else that you have to do. You don't have to calculate. You even don't have to go through that list like I just said, because the Roman numeral tells you the charge. So you write it down and you're done with the cation. In this case, the anion, hydroxide, I guess this is another one that's IDE in addition to cyanide. But hydroxide is one of your polyatomic ions. Again, I hate to say this, but you really do just have to memorize the polyatomic ions. I don't like to have to tell you to memorize things. This is one of the few things, the 18 or 20 of those polyatomic ions, that you really do just need to know. So assuming that I know what it is, hydroxide has the elements, or the atoms, OH, and it has a charge of a -1. Remember that with our charges, plus or minus, if the value is 1, we leave off the number and we only write the sign. So I've done this critical first step of writing the ions, including the charges. And now I'm going to ask the same question that I did last time. I'm going to ask the question, are the charges equal and opposite? So I'm comparing a 6 to a 1. And I want to know, are those numbers the same? Again, the answer is no. So because the answer is no, I'm going to have to do that same sort of swapping with the value of the charge becoming the subscript for the opposite ion. So in this case, the 6 is going to swing over here to be the subscript for hydroxide, and the 1 will go over here to the chromium. Because that first subscript is a 1, we don't do anything with it. We just leave that off. So the chromium will still be just Cr. We leave the 1 off. And hydroxide, OH, and it will take on the subscript of 6. With our polyatomic ions, if you only have 1 of the ion, you do not include it and enclose it in parentheses. But here, I have 6 of them, so I have to include, I have to enclose the chemical formula of the polyatomic ion within parentheses. So the O and the H are within parentheses, and that 6 goes on the outside. So the correct formula for chromium 6 hydroxide is Cr parentheses OH6. Let me show you what's wrong. And I'll put a big X through it so you don't mistakenly think it's right. If I do this, it's wrong. Because in the correct version, both the oxygen and the hydrogen have have the multiplier of 6 applied to them. And so this correct chemical formula is telling me I have 6 oxygens and 6 hydrogens. This incorrect notation for this formula tells me I have 1 oxygen and 6 hydrogens. Because the parentheses aren't here, that 6 isn't applying all the way across. So make sure when you have a polyatomic ion, I'm going to say it again, and you have more than 1, in other words, you have a subscript attached to that polyatomic ion that is a 2, a 3, a 4, a 5, a 6. You have to make sure you enclose the whole thing in parentheses, the whole polyatomic ion. So we'll move on to our last example of named a formula. And we have magnesium carbonate. Okay, so we're going to just go through our rules the same way that we have before after we color code. So our cation is magnesium, our anion is carbonate. So our first step is to write down what these ions look like in terms of symbol, chemical formula, charges. Magnesium has the symbol Mg. We don't see a Roman numeral here, so that tells us this must be one of the fixed charges. So we go through our list. Group 1A, 2A, 3A, cadmium, zinc. Magnesium is in group 2A, so it has a charge of 2+. Carbonate is a polyatomic ion, and we know now that we just need to know them. And it has the chemical formula CO3 with a charge of 2-. Continuing through our same process, we're now going to check, are the charges equal and the signs opposite? Of course, the signs are opposite. We want to know if the values are equal. So the question is, does the 2 equal the 2? Now the answer is yes. The charges are equal and opposite, 2+ and 2-. And when we have that situation, we don't swap out the charges. In other words, because 2+ plus 2- equals 0, we just combine these 1 to 1. And what that means is we just write down the formulas without the charges. So we write down Mg CO3. So this is the correct formula. Let me show you what would be wrong and how we fix it. Let's say that you forgot to do this step. I know you're not going to forget to do this step because you're going to check that are the charges the same every single time. But let's say you forgot and you went ahead and did the swapping out of the charges anyway. If you had done that, you would end up with Mg2 CO3 2. Now this is this is an incorrect chemical formula. It is not the correct way to write this chemical formula, and that is because when you look at the subscripts, and I'm talking about the multiplicative subscripts, in other words, not the 3 in the carbonate, I'm talking about the subscripts that are used to indicate you have more than one of the ion, so the 2 and the 2. One of the things that we should be doing is taking a look at our final chemical formula and deciding, can we reduce those subscripts? And in fact, we can with this chemical formula. We can divide both of those subscripts by a 2 and reduce them. And when we do that, we end up with MgCO3. So while the way that I wrote this with the 2's in place is incorrect, if you had done that, you can fix this by recognizing that you can reduce those subscripts and ultimately end up with the correct formula. And that's something really that you should check anyway. Most of the time you won't have to do this reducing. Every once in a while though you will. Now let's go the other way. Now let's start with chemical formula, and from the chemical formulas write the names. I didn't mention this earlier, but because I clearly separated these problems into molecular work and ionic work, But on an exam, you're going to see just a whole bunch of nomenclature problems, right? You'll see some names, you'll see some formulas, and that first important step is to check what kind of compound are you dealing with, so that way you apply the correct set of rules. So in other words, so you apply the prefixes like di and tri for molecular compounds, and so you deal with ions and charges with ionic compounds. When we assess the type of compound, and this is shown in sort of a flowchart list in activity 13, the first thing you look for is if the first part of the formula is a metal. And if the answer is yes, if it's a metal, like zinc, like chromium, like magnesium, our first three examples were metals, then those are ionic compounds. If the first element is a metal, the compound is ionic, and you know that, and then you move on and apply the correct set of rules. If the first part of the compound is not a metal, the second question is it ammonium? And so you're either literally looking for the word ammonium, or you're looking for the chemical formula for ammonium. In this case, even though every single element here is a nonmetal, the fact that this starts with ammonium tells us that it's ionic. So you look for a metal, or you look for the chemical formula for the polyatomic ion, NH4, and that tells you that the compound is ionic. We already knew it was ionic because I had said these are ionic compounds, but I just wanted to point out how you do that check, and that check is very, very fast. So rewriting our chemical formula in terms of cation, then anion. So the NH4 part is our cation, and the SO3 part is our anion. When you have polyatomic ions, this is one of the things that you get better at with practice, and that is, this is a whole bunch of elements, and it kind of maybe looks a little bit like a mess, and so you have to learn how to pick out which collections of atoms are polyatomic ions, and that really does come with practice. So I've rewritten this with the color codings, and you don't have to use color coding. I do this so that way it's hopefully clearer what I'm talking about, but you don't have to do that. So I have my chemical formula, and the next thing I want to do is simply write the symbols or molecular formulas in this case for the ions and write their charges. Now I already did that with the other set of examples. I need to do it here. Even though I already have all the symbols and such, I need to write out these ions very clearly, because once I do, the final step between chemical formula and name is really straightforward. But what we're doing right now tends to be the tricky part. So if you can figure this part out and get it right every time, that final step where you write the name becomes pretty easy. So when I do this, I'm going to ignore the subscripts. Now I can't ignore the subscripts that are already part of a polyatomic ion, but I'm going to ignore this 2, because this doesn't tell me anything about the cation itself. It only tells me how many I needed to combine with the sulfite to get charge neutrality. So my formula for ammonium is NH4. It's a polyatomic ion that we've already established. We just need to know. And it has the charge of a plus 1. The rest of this is my anion, SO3. and it has a charge of a 2 minus. So remember, I started with chemical formula. So I'm not rewriting this formula, but I am taking now these two distinct ions, and I'm simply going to write their name. So NH4 plus is ammonium. I leave off the word ion whenever I might have had the word ion for standalone. Ion, I leave it off, so it's ammonium. That's the cation name, and a space. And my anion name in this case was sulfite. Ammonium sulfite. I'm going to say it again. This step right here, writing the correct cation and anion with their charges, writing that completely, and then writing the name makes this process much, much easier. And this one is done. So we'll move on to our next example. NiS. So I'm going to color code my cation and my anion. And then I'm going to write down the symbols. So the symbol for the cation is Ni, and the symbol for the anion is S. So this is kind of the opposite of the previous example. The previous example, both ions were polyatomic ions, and in this example, both ions are monatomic ions. So I don't even have one polyatomic ion here. I run through my list now of determining my cation charge. So I run through my list. Group 1A, 2A, 3A, cadmium, zinc. Nickel does not fall into those categories. So that means I'm going to have to figure out the charge. So let me say this again. If the cation does not fall into group 1A, 2A, 3A metal, cadmium or zinc, then it is one of the variable charge ions, and we have to figure out the charge for this specific cation. The other part of this, S, when it's an ion, always has a charge of 2 minus, and you get that from the periodic table, and we talked about that earlier. So now I have to figure out what is the charge on the nickel, and we do this mathematically. Okay, so the sum of the charges has to equal 0, and it doesn't matter if I start with the cation part or the anion part. I just have to connect them correctly. So if I look back at my original chemical formula, my subscripts were 1s. There was a subscript of a 1 attached to the nickel and a subscript of 1 attached to the sulfur. So when I do this math, it's 1 times the X plus, what I'm trying to figure out, plus 1 times the 2 minus, that one I know, and the sum of those charges has to equal 0. So I end up with X plus, try this again. X minus 2 equals 0, and that gives me X equals 2 plus. So the charge on the nickel is a 2 plus. So I have nickel 2 plus, and my S2 minus didn't change. I now have that critical part done, which is writing the ions and their charges, and now I simply name them. So metals the metal ions always take on their full metal name. And if it's a variable charge, which this one was, then I have to tell the world what is the charge. And the charge is shown as a Roman numeral. How do I know what the what number goes there? It comes directly from that 2. So whatever that charge is that I figured out, that I calculated, that number becomes the Roman numeral in parentheses. And in this case, nickel 2 is a single word, and it is the single word for my cation. I then have a space, and now the name of the anion, which is sulfide. Cation name, anion name, nickel 2 sulfide. And we have one more example. Al2O3. So my cation is aluminum. My anion is oxygen. Al2O3. Okay. So now I need to write my cation with its charge, my anion with its charge. Aluminum has the symbol Al. And now I run through my list. Group 1A, 2A, 3A, cadmium, zinc. Aluminum is group 3A, so it has a charge of 3+. It's one of the fixed charges, but you need to know what it is. Oxygen, when it is an anion, it has the symbol O anyway, but as the anion, it has a charge of a 2 negative. So I've now written my ions with their charges, and now it's just a matter of writing cation name and anion name. The cation name of aluminum is just aluminum. If this ion, if aluminum was a standalone ion, I would include the word ion. But when it's part of an ionic compound, we remove the word ion. So the cation name as part of the ionic compound is simply aluminum. I do not include a Roman numeral with a 3 because aluminum is always a 3+ when it's an ion. It is never anything else. You only include the variable charges as Roman numerals in parentheses. So I just leave this as aluminum. It's not more right if you add the 3. It's actually wrong, so don't add it. Cation name is aluminum. Anion name is oxide. So the name of Al2O3 is aluminum oxide.